Hi, this is our second day in lesson 4.2, which is about the unit circle. Today we're going to be talking about the trig identities, or some of them. An identity is just an equation that's true for all values of the variable. Like I showed the distributive property, and I can call that an identity because no matter what you use for x, a, and b, x times the quantity a plus b is equal to xa plus xb. There are lots and lots of trig identities. Today we're going to look at some of the basic ones, and we're going to begin with someplace that we were before. We've learned that you can call functions even or odd based on some criteria. The criteria may look different to you now than it did earlier. We really didn't need this definition earlier. But if a function is even, then the value of the function at the opposite of x is the same as value of the function at x. Okay? Even functions, when you put negative x into the function, you get the same output as if you put positive x. In a similar way, if you have an odd function, then when you put in the value of the function at negative x is equal to the opposite of the function at x. Or when you put in negative x, you get out the opposite of what you'd get when you use regular x. The cosine of angle t in my picture is equal to, remember we're in the unit circle, and the coordinates of point P here are x and y. So this is x and this is y. The cosine of t is x. Okay, that's the side adjacent. If we look at the cosine of the opposite of t, this angle, the cosine is still the same. It's still x. That means that the cosine is an even function. And I'm just looking at those definitions one more time. When I use the opposite of x in the function, I get the same thing as if I use the regular x. And that's exactly what cosine does. The sine in this picture is the y value. And if we go to the negative angle, we don't get y anymore, we get the opposite of y. That means that the sine function is odd. And how those things are going to help us, well, I don't know if we'll remember the rules, but I know that we can draw the pictures. So I depend on the pictures a lot, and I want to show you what I'm talking about here. Even and odd functions are supposed to help us find a value for the secant of negative pi fourths. A picture might be in order. I'm not going to draw the circle, but I am going to say negative pi fourths is negative 45 degrees. So that's our angle right there. And I know that secant and cosine are the ones that go together. So since cosine is an even function, then the value of cosine at pi fourths is the same as the value of cosine of negative pi fourths. X is the same in both of those places. So I know that this is going to be the same thing as the secant of positive pi fourths. And I know that that, folks, is the reciprocal of the cosine at pi fourths. Now, this may look convoluted to you, but if we're pi fourths, that's 45 degrees. So this angle and this are equal. And both of these pieces are root 2 over 2. One we want is the x one, root 2 over 2. So let's see. 1 over, and the cosine of pi fourths is root 2 over 2. And I don't like that nasty looking fraction. I'm going to multiply by the reciprocal. And that's going to get me 2 over root 2. When you simplify that, you're going to have 2 root 2 over 2, and that cancels to the square root of 2. So all that said, the secant of negative pi fourths, which is this angle, is the same as the secant of the positive pi fourths angle, and both of those are equal to the square root of 2. Whew. All right, the tangent function at negative pi fourths. Well, we have the picture for negative pi fourths going on right here. We know that the y in this one is negative, and x is root 2 over 2. Y is the negative of that. Tangent is y over x, so it's negative root 2 over 2 all over root 2 over 2. Guess what? That's negative 1. Any number divided by itself is 1. we're going to talk next about the reciprocal identities. And we kind of have already touched on it. We've used the term reciprocal a lot. The sine of some angle t is the same thing as, or is, the reciprocal of the cosecant. Remember, each of the pairs has one co in it. The reciprocal of cosine is the secant. The reciprocal of tangent is the cotangent. And vice versa. There we go. The reciprocal identities. The quotient identities, folks, are going to be important to us. And remembering that the tangent of an angle, I'm going to come up here, the tangent of an angle is its y over its x, right? Because it's opposite over adjacent. So the tangent of any angle t is y over x. That's a quotient or a division. The cotangent is the reciprocal of that, x over y. So this is true. The tangent is y over x. But folks, if you think about that in the greater scheme of things, remember that y in the unit circle goes with the sine. We could say that the tangent of t is the sine of t over its cosine, y over x. Same thing is true here. This would be cosine of t over sine of t. And those are very, very important identities. Okay, let's see how we can use those to our advantage, hopefully. We've got an angle t whose sine and cosine we know, and we're to find the values of the other four functions. I am a creature of habit, and I have to write them all. So the sine of t was given to us as 2/3. That means that the cosecant, which is the reciprocal function, would be 3 over 2. The cosine in this angle is root 5 over 3. The secant of that same angle will be 3 over root 5, and we know where this is going. That simplifies to 3 root 5 over 5. Now the tangent, y'all, we just said on the other page that tangent is y over x or sine over cosine. So I'm going to use sine over cosine and say that it's 2/3 divided by root 5/3. We know that simplifying, the 3's go away, and we're looking at 2 over root 5, which simplifies to 2 root 5 over 5. The cotangent is going to be a lot easier. It is cosine over sine, so root 5 over 3 all over 2 over 3. Denominators are the same. So root 5 over 2 is the cotangent. So we wrote all 6 trig functions just from knowing 2 of them. That's pretty cool. And we did that with those reciprocal and quotient identities. We'd like next to talk about the Pythagorean identities. And folks, I need to draw myself a picture. So excuse me while I do that. We're talking about some point that's on the terminal side of an angle whose coordinates are x and y, and what that means for us is that that's x, that's y, and that's 1. Folks, that's a right triangle right there. You know that the unit circle is defined by the equation x squared plus y squared equals 1 squared. That's the Pythagorean theorem for this unit circle. Because the cosine of the angle is its x value and the sine is its y value, it follows that you should be able to substitute. X is the cosine of t, so the cosine of t raised to the second power plus the sine of t raised to the second power equals 1. That's just substituting what we know. Normally this is written in a slightly different form. It means the same thing. They usually talk about sine first, so they would say that the sine and then squared of t plus the cosine squared of t equals 1. Those two are equivalent statements. It's just a different way of writing the squaring. The Pythagorean identity is an important one and one that you'll use over and over in class. In fact, it gives birth to two other Pythagorean identities. They can be found by dividing each of the terms by either sine squared or cosine squared. And I'm going to start out with sine squared. Sine squared, that's 1 right there. Cosine squared over sine squared. Cosine squared over sine squared, that's the cotangent. So cotangent squared of t. And 1 over sine squared, well, the reciprocal of sine is cosecant, so this must be cosecant squared t. And there's another Pythagorean identity. Comes from the big one, right? If we can remember the big one, then we can get the other two. To find the other variation of this, instead of dividing by sine squared, divide by cosine squared. And sine squared over cosine squared is the tangent. Sine over cosine, tangent. So tangent squared of t. Cosine over cosine, that's 1. And 1 over cosine is secant. So we've got 3 Pythagorean identities that all come from the same main one. Sine squared t plus cosine squared t equals 1. This problem is an interesting one. It says if we know that the sine of some angle is 1/2 and the angle t is between 0 and pi halves, that would be 0 and 90 degrees. What we want to do is find the value of the cosine using the Pythagorean identity. Well, Pythagorean identity says sine squared plus cosine squared equals 1. And we know a value for the sine of that angle. It's 1/2. 1/2 squared plus cosine squared has to equal 1. And 1/2 squared is 1/2 times 1/2, that's 1/4. 1/4 plus cosine squared, I should put the t in there, equals 1. We want the cosine, that's what we're trying to get to. So cosine squared of t will equal 1 minus 1/4, that's 3/4. And if we take the square root of both sides, the cosine of t is going to equal the square root of 3 over 4, which is the same thing as the square root of 3 over 2. You can take the square root on the bottom. That's kind of a tricky thing right there. Given the sine of the angle, we came up with the cosine simply because we know that sine squared plus cosine squared must equal 1. Lastly, what we want to think about, since we know that that point P can rotate many, many, many times around the circle, you can define periodic properties of the trig functions. How many radians does point P travel through in one complete rotation? Well, you know, it's 2 pi. After one or more revolutions, the coordinates of P are the same, exactly the same. So the sine of t plus a full revolution is equal to the sine of t, and the cosine of t plus a complete revolution is the same as its cosine. You can say then that those things, sine and cosine and the reciprocals, are periodic, that is, they repeat, periodic, and that their period is 2 pi radians. You can show that the tangent has to have a smaller period than 2 pi. If you rotate the point P pi radians, what's going to happen? The x, the value of the x in absolute value is the same, but it's the opposite sign. Same thing for y. So this is the point negative x, negative y. And the tangent of t is its y over its x. If you think about the tangent of t plus pi radians, it will also be negative y over negative x, which is the same as y over x. That is, we get back to exactly the same thing, and all we had to go was pi radians. The period of the tangent function and cotangent is pi radians, because it only takes them a half turn before they become the same values again. To wrap it up, remember that you can do many, 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 many rotations, infinitely many. So instead of just saying plus 2 pi, we can say 2 pi n, where n is some integer. So in all of these, n is an integer. And if the sign at t plus 2 pi n, any number of full rotations that I add on there is also going to be the sine of t. It has a period of 2 pi. The cosine, no matter how many times I revolve, as long as it's an integer number of times, the cosine of t plus many rotations is the same as the cosine of t. And here's our tangent. The period is pi now, not 2 pi. But no matter how many times we multiply by pi and add that many half turns on, we're going to end up with the same tangent. So there's a glimpse at some of the basic trig identities for you today. Get out there and do that U-try. Remember, that's your job before school tomorrow.